Watch the wing, not the flaps, not the ailerons, the entire wing, sweeping backwards while the aircraft is in the air and nobody in the cockpit asked it to. An aeroplane is normally one compromise, frozen in metal, fast or slow, short landing or long range. Whichever the designers picked, the airframe lives with that decision for 30 years. These 9 refuse to pick. Every one of them changes its own geometry in flight, and every change buys back something the fixed shape had to give away. 8 of them worked, 1 never got the chance to find out. The Tomcat is the version everyone has seen. Its wings sweep from 20 degrees spread to 68 degrees back, and the gap between those 2 positions is the gap between 2 completely different aircraft. Spread wide, the wing is long and efficient. It makes lift at low speed, which is exactly what you need when the runway is a moving ship and the approach has to be survivable. Swept back, that same wing becomes short and sharp. Drag falls away at high Mach, and the shockwave stops tearing at a long span that was never built to sit in supersonic air. The clever part is not the hinge, it is that the pilot does not work it. A computer reads Mach number and altitude and moves the wings on its own schedule continuously without being asked. A pilot can override it. Almost none did because the machine was better at it. The sweep is right at every point in the envelope, rather than at the 2 or 3 settings a human would bother to select. There is a third position that has nothing to do with flying at all. On deck, the wings oversweep to 75 degrees, past anything aerodynamic, purely so the aircraft takes up less of a hangar. And there is a fourth surface most people never notice. Small vanes slide forward out of the wing root at high speed, shifting the aerodynamic center forward to keep the aircraft controllable as the shock moves aft. So the Tomcat is not one airplane that adjusts. It is a slow-speed aircraft, a high-speed aircraft, and a parking problem, and it converts between all 3 in the air. It cost weight to do it. A swing wing needs a pivot strong enough to carry the entire bending load of the wing through a single joint, and that pivot is titanium, heavy, and a permanent structural penalty the aircraft carries even when the wings never move. The Navy accepted that penalty for 32 years. The Tomcat left American service in 2006, and the only Air Force still flying them is Iran's, keeping a handful airworthy from a batch delivered before 1979. The Tomcat moves its wing, the next aircraft bends it. This FA-18 was given a wing deliberately built too thin and too flexible, the exact property every structural engineer spends a career trying to design out. A flexible wing twists under load. Deflect an aileron to roll, and the force of that aileron twists the wing the other way. Above a certain speed, the twist wins, and the aircraft rolls in the wrong direction. That is control reversal. The standard fix is to make the wing stiffer and heavier until it stops happening, and then to carry that weight for the rest of the aircraft's life. This program did the opposite. It kept the wing flexible and used the leading edge to twist it deliberately, turning the whole wing into the control surface instead of fighting it. The wing is not carrying the ailerons anymore. The wing is the aileron. Twist it a degree, and the entire span changes its angle of attack at once. The payoff is weight. A wing that does not have to resist its own twisting can be thinner, lighter, and lower in drag, and the flexibility that used to be a structural defect becomes the mechanism. This was not a paper study. A real FA-18 flew it in 2 blocks of flight testing between 2002 and 2005, with the wing instrumented to measure how much it was twisting and how much roll that twist actually produced. It worked, and the reason you have not heard of it is that the result was not an aircraft. It was a design method which went quietly into the way later wings are analyzed, rather than into anything you can point at on a ramp. Both of those change the wing's shape. The third changes the angle the wing is bolted on at. The Thunderceptor has a wing that is wider at the tip than at the root, which is backwards from very nearly every aircraft ever built. A normally tapered wing stalls at the tip first, and a tip stall takes the ailerons with it. Making the tip the widest part keeps the outer wing flying after the root has already given up. Then there is the incidence. The whole wing pivots relative to the fuselage through about 5.5 degrees in flight. The reason is landing. A fast interceptor wants a low-drag wing at altitude and a high angle of attack on approach, and normally you get the second by pointing the entire aeroplane nose up until the pilot cannot see the runway. Pivot the wing instead, and it reaches its landing angle while the fuselage stays level. It also carried a rocket engine in the tail on top of its jet, because an interceptor's whole job was to be at altitude before the bombers arrived, and a turbojet of that era simply could not climb fast enough on its own. 2 were built. It is often credited as the first American fighter to pass the speed of sound in level flight, a claim that depends entirely on how generously you define level. Neither aircraft led to a production order, and the inverse taper wing was never used again. So far, the wing moves as one piece. The next 3 aircraft take part of themselves out of the airflow entirely. The Valkyrie is a 6-engined bomber close to the size of an airliner, built to cruise at 3 times the speed of sound, and the outer 6 meters of each wing folds downward in flight. Fully deployed, the tips sit 65 degrees below horizontal. It looks like damage. It is the largest moving structure ever fitted to a wing. At Mach 3, the aircraft is riding on its own shockwave. The wedge inlet under the fuselage throws a shock backwards, and the underside of the wing sits on top of that pressure. That is compression lift. Lift for free from a shockwave the aeroplane made itself, but only if the pressure cannot escape sideways. Folding the tips down builds a wall on each side, and the high pressure stays trapped under the wing instead of spilling off the end of it. The tips do a second job at the same moment. A delta this large has very little directional stability at high Mach, and 2 large vertical surfaces at the extreme ends of the wing work as fins. One hinge buys lift and stability together and costs nothing at low speed because the tips simply stay up until they are needed. Moving those tips was not free either. The hinge, the actuators, and the structure to carry the load through them ran to roughly 3 tons per side on an aircraft already fighting for every kilogram. 2 were built. One was lost in 1966 when a chase aircraft flying formation for a photograph drifted into the wingtip and took the vertical fins off. The other one is in a museum in Ohio, tips up, where it has sat ever since. The Valkyrie folds its wingtips to trap pressure. The Buccaneer splits its tail in half to throw pressure away. The very back of the fuselage is not a fairing. It is 2 clamshell halves, hinged, and they open sideways into the airflow like a pair of doors. A conventional air brake is a panel on the wing or the side of the fuselage. Open it and it disturbs the airflow over everything behind it, which on a low-level strike aircraft means the tail. Putting the air brake at the very end of the aeroplane solves that completely. There is nothing downstream left to disturb. The Buccaneer needed this more than most. It was built to fly at wavetop height at high subsonic speed, where a small change in drag is the difference between hitting the target and hitting the sea. It also had to land on a carrier. A carrier approach is flown on the back of the drag curve with the engines well up, and the air brake gives the pilot a way to control speed with the throttle instead of the attitude. The halves open symmetrically, so all that drag acts on the center line and the aircraft does not yaw when they deploy. The result is an aeroplane whose tail is a working door and which can change its own drag by a large factor without moving a single conventional control surface. It is worth saying how long that arrangement lasted. The Buccaneer entered service in 1962 and was still flying combat missions in 1991, marking targets over Iraq, 3 decades after a design decision to put the air brake where nothing could be upset by it. The Valkyrie folds, the Buccaneer opens, the U-2 throws part of itself away. It has a wing of enormous span on a fuselage that is very nearly a glider, and it has to get that wing off the ground without carrying the landing gear that would normally hold it up. The main gear is a bicycle arrangement, 2 units on the center line, 1 forward, 1 aft, which leaves the wings completely unsupported. So the aircraft takes off on outriggers, small-wheeled struts under each wing, called pogos, not attached to anything permanent. As the wing takes the aircraft's weight, the outriggers unload and simply fall out. They are left lying on the runway, and the aeroplane climbs away having shed a part of its own landing gear. Landing is the problem this creates. There are no outriggers left. The aircraft has to be held level on 2 centerline wheels until it runs out of speed, and then one wing has to go down. The wingtips carry skids for exactly that moment. The aeroplane lands, balances as long as it can, then leans over and drags a reinforced skid along the runway, and a ground crew walks out and bolts the pogos back on before it can taxi. The whole arrangement exists to protect one number. Every kilogram of landing gear is a kilogram not spent on span or fuel, and span and fuel are what put the aircraft above 20 kilometers where nothing could reach it. The aeroplane first flew in 1955, and it is still in service. 70 years of an aircraft that cannot support its own wings on the ground, because being light enough to fly that high mattered more than being able to taxi. Those three take something away. The last three change what the aircraft fundamentally is. This F-15 has a lance on the nose that is nearly 8 meters long, and it grows. It telescopes in flight in 3 sections from about 4 meters retracted to close to 8 meters extended. The target is the sonic boom. A supersonic aircraft pushes one strong shockwave off its nose, and by the time that reaches the ground, it is rolled up into the double bang everyone recognizes. The spike does not stop the shock, it splits it. Each step in the telescoping structure throws its own weak shock, and several weak shocks are far harder to merge into one strong one. What arrives at the ground is a rumble instead of a crack. Not silence, the energy has to go somewhere, but spread out rather than concentrated into a single front. It is a shape change with no aerodynamic benefit whatsoever. The aircraft does not fly better with it fitted, it simply makes less noise for the people underneath. The reason anyone cared is regulatory rather than technical. Overland supersonic flight has been banned across most of the world since the 1970s, not because of the speed but because of the noise, and no amount of engine work fixes a shockwave. It flew around 50 times on that F-15, and the shape held together at Mach 1.8, which was the open question. The idea did not stop there. An aircraft shaped from nose to tail around exactly this principle is flying now, and it exists because a telescoping lance proved the shocks really could be kept apart. The spike changes what the aircraft sounds like. The Harrier changes which way it is going. 4 nozzles, 2 each side, rotate through about 98 degrees, from pointing straight back to pointing straight down to slightly forward of straight down. The engine itself never changes. It makes the same thrust it always did, out through a cold fan duct and a hot exhaust duct, and the nozzles simply decide where that thrust leaves the aircraft. Pointing down, it hovers. Pointing back, it flies. Everything between is a transition, and in that region, the wing is not yet making enough lift, while the nozzles are no longer making enough thrust. That transition is the dangerous part of flying a Harrier, not the hovering, which looks harder and is not. Then, there is the use nobody planned for. Vector the nozzles partway down while flying forward, and the aircraft decelerates hard and pitches in a way an aeroplane with fixed exhausts simply cannot. Pilots called it viffing, and in a turning fight, it lets a slower aircraft suddenly stop being where its opponent expected it to be. It earned the argument in 1982, operating from ships in the South Atlantic, where there was no runway within 1,000 kilometers and no possibility of building one. And the trade is honest. 4 rotating nozzles in the middle of the fuselage means the engine has to sit at the center of gravity, which dictates the entire layout of the aircraft around it. Everything else about a Harrier is downstream of the decision to let the exhaust point wherever it likes. Every aircraft so far actually did the thing it was built to do. The last one did not. This is a helicopter with wings and 2 jet engines, and the intention was that the rotor would stop turning in flight. A helicopter is efficient in the hover and badly limited in forward speed because the advancing blade runs towards the speed of sound while the retreating blade runs out of airflow altogether. An aeroplane has precisely the opposite problem. It is fast and it cannot hover at all. The X-wing was meant to be both. Take off as a helicopter, accelerate on the jets, then slow the rotor and stop it, leaving 4 rigid blades locked in an X, working from that moment on as a fixed wing. A stopped rotor has no ailerons, and its blades are symmetrical, so lift was going to come from blowing compressed air out of slots along the blades, steering the airflow itself rather than moving anything. The aircraft flew. The rotor was never stopped in the air. The program was canceled in 1988 with the conversion, the entire point of the machine, never once tested in flight. The problem was never the aerodynamics, it was that the moment of conversion has no margin in it. A rotor slowing through the speeds where it is neither a working rotor nor a working wing is, for a few seconds, an aircraft held up by nothing in particular. Every other aircraft here changes shape with a reserve underneath it. The Tomcat still flies with its wings anywhere. The Harrier in transition still has an engine. Stop a rotor in midair, and there is no configuration to fall back to, which is why it was studied for a decade and never once attempted. 8 of these worked. The sweep, the twist, the pivot, the fold, the clamshell, the discarded gear, the growing nose, and the rotating nozzle all did what they were built to do, and several of them are still flying. What they share is a refusal to accept that an aircraft has to be one shape. Each of them decided the compromise was negotiable and built a hinge, a pivot, or a slot to prove it.